All right. Good evening, everyone. I hope you can all hear me well. So the session is being recorded and I will start by sharing my screen. Okay. All right. So welcome. Welcome to the second live session. Here we will be discussing week 3. So I hope you've all seen the videos from week 3. So I'll quickly go through some of the basics and then we'll shift to RStudio for what's lined up for today. You can interrupt me anytime in between, unmute yourselves or ask in the chat box, and then we'll clear your doubts. Okay. All right. So the last live session was conducted on 4th of Feb. That was a Saturday where we discussed week 1 and 2. The recording has been uploaded to YouTube at this link, and it's also shared on the NPTEL portal. So, right. Can you all confirm if you have already installed R and RStudio?
Yes, ma'am.
All right, great. So now the first thing that, and a couple of you also asked on the discussion forum, was where to get the files and the scripts that sir used in those lectures. So I'll quickly show you where we can access those. There are two ways. One is that it's there below each of the NPTEL videos. So for week 3, a total of 4 lectures, 3, 4, 5, and 6 had these scripts or documents or CSV files. So there's a link right below. So let me just, 1 second. Yeah. So, right. So here, if you see, for example, I've opened lecture 3 from week 3. So here is the download link. So if you open it here, code data lecture 3 week 3, you click here and you have each of these files. So you can just click and download them. All right. Another way to download them could be from GitHub. So GitHub, this is a page where people upload their codes and the files, and that's available to the public. So sir has uploaded this. He has shared the link in one of the discussion forums answers. So you can click this, and once you click, it will be downloaded as a .rar file. For Windows, there's a WinRAR app that you can use to sort of uncompress it, or you can also use any of the online RAR extractors for this. All right. Okay. So with that done, so any question till now? I hope you will all be able to download the files and the scripts, right? Keep saying yes or no so that I know you're all still with me.
Yes.
All right, great. Fine. So this is what RStudio looks like, right? There are 4 major panes here. The source pane, the console or the command prompt, the environment here, and the output. So as it was mentioned in the lectures, that this is where we would be writing the commands, but not executing it. So let's say you wrote a command and you want it to be with you. You don't want it to go away once you close the session. So here you can see here, I have a script open. It's untitled at the moment. It's open. I'm going to type it and then I'm going to save it. And each of the commands I can execute here in the console or the command prompt. And as and when I keep executing it, I'll have some variables that are going to be created. These would be saved in the environment. And the different scripts that you have, the different commands that you execute, they're going to be certain plots that are generated. Sometimes you may want to know about a command, and we'll see in today's lecture how to use the help option, how to install packages, and how to navigate through files that are there in your system. All right. So R, as we know, it's a command line programming language. We have seen what is the difference between the R script and the command prompt. So you write, you save it, and then you can load it again the next day when you want to rerun or revisit those commands. And yes, you need to save the script. So one of the major things is the directory. So right, so the directory is where your RStudio can directly access the files from. So as let's say in Windows, you have a D drive and then you made a folder in your name. And then you made, okay, NPTEL noc23-bt26. And then you say, okay, week 1. So these are directories or folders, as we say. So let's say today you are working with in a folder that's named week 3. The next time we meet, maybe you want to work in a folder that's named week 4. So to directly access the files that are there, it's very important to set the directory. So there are 2 ways to set it. We'll see in the lecture today. And we'll see where this comes from. I think I'll shift to RStudio and show you some of these other things. So if I can open these side by side, that would be good. All right. I hope you can still see the screen. So if you take a look here it says R4.2.1 and a path, right? So here this is the version of R, and here it shows the working directory. So I have a working directory somewhat, and it says week 3. So finally I am able to see the files that are present in week 3. If I want to change the directory, I can go into session and I can say set working directory. Set working directory and then choose a directory. So it will open this pane so I can navigate and then I can set that. Another way to set is this set WD. So take a note here, set WD, and it's a command, right? So a command in R is always followed by these curved brackets or round brackets. So we say set working directory, and then I don't really know how to type inside this. So what I should do is put a question mark before this command, and let's see what I think. I'll just close this for a while. Okay, so if you see here, all right, so if before any command, before any function, if I put a question mark and I press enter, so you see this toggle to the help menu, and it says get or set working directory. It has a description of the function, how to use it, and what are the arguments. So anything that goes inside the function, inside this command, is an argument. Some functions can have a single argument, some can have multiple arguments. If there are multiple arguments, some of them may be necessary to be specified, some of them are optional. So as we move on and as we see more and more commands, we'll see which of them are compulsory, which of them are optional. So here it says an example also, and then it says directory, it's a character string. So in R, whenever we write a character, it's always supposed to be in double quotes. So this is how I can specify. So let me just retype the whole thing. And if in R, one of the best things is to use the tab, which is just above caps lock. If you press tab, it is going to predict all the possible options. So now I know I need to go into documents and so on. And I specified these. If I would have not given this one, then you see here it's changed. And if I want to retype this thing, I can either copy and paste, or what I can do is press the upper arrow. So when I press the up arrow once, and then twice, and come back to this. So look here, when I press enter, the working directory has changed again. Okay, with me till here, everybody? I hope you're all there. Yes, okay, thank you. All right, so now so you can see here, everything that you can see right now has the first character everywhere is a hash. The symbol just above 3, right? So shift 3 gives you this hash symbol, and this is used for a comment. So a comment is anything that you don't want R to execute. It is for your own information, so that if a month or 2 later you revisit your script, you understand, oh, this is why I typed it here. This is what the step is doing. Because as you can already see here, we have some 300 lines of codes. right? So I'm going to forget which one means what. So I've added comments after every few lines to remember what each of the steps is doing. This is a good practice, and the more you can add comments, the better it is. All right. So initially, I have sort of summarized all the commands that we used from lecture 2 to 6 of week 3. The first lecture only had introduction to R and R Studio. So I will quickly skim through these. If you think you want me to emphasize on any one of these, let me know. I have made a few changes, but most of these are very similar to what you've already seen. All right, so lecture 2 initially talked about these arithmetic operators, plus, minus, divide, multiply. So here I have typed, but here right now I don't know the output. So when I want to know the output, I can select it and I can press Control Enter, Alt Enter, or in Mac, Command Enter, anything, and it will get executed. So what execution means basically is I am copying it. So I have pressed sort of copy, and here I'm going to paste it, and I'm going to press Enter. This is one way of doing it. Otherwise, if I just sort of have my cursor on this line, or I select the whole thing and I press Control Enter, even then it's doing the same thing, right? Another way of doing it, as was mentioned, was to highlight it and press the button Run. Each of these ways, your commands that you have in the script, they get copy pasted and enter in the console. So it's known as the command has been run or it's been executed. Likewise, you can do it for all of these. Now, these outputs are not stored. You can see that, okay, I executed 2 plus 3, and I know the output is 5, but I don't have it saved anywhere. If I want to use this output somewhere, I cannot really use it. So there comes the assignment operator. So variables are what you can use to save some information. They can be numbers, they can be characters, they can be tables, they can be really anything that you want to work on. So let's execute this one. So anytime I'll just highlight, and if you see this getting pasted in the console, it means I've pressed Command Enter or Control Enter, right? So 5 is assigned to X. So here it's towards the left side. The arrow is towards the left side, which means the value 5 is getting assigned to X. So you can see in the environment X, and the corresponding value is 5. So now if I just press X, so this value comes right here. Okay. Another way, so again, Y and Z. So another question was asked in one of the discussion was that what is the difference between is equal to and the assignment operator? So in this case, there is no difference. It is a matter of choice whether you want to use the is equal to sign or the assignment operator. But there would be certain cases, as we'll see today, where using one may be better than the other. So mostly the assignment operator is preferred because the is equal to is used somewhere inside the function, as we'll see as we move on. Okay, so here we have executed these commands. So we see that we have values corresponding to 3 of these variables, right? So these 3 variables are now a part of our global environment. Now, so commands in R, you can identify it's a command if there is some name and it's immediately followed by a round bracket, no space in between, right? So here, and generally the names of the commands would be somewhat self-explanatory, that what they are doing. Function command names are not going to be ABCD. So it's always better, even when you are naming your variables. Here, for example, I've named it XYZ, but suppose when you work and you're working with a lot of variables, it's always preferred that you name the variable appropriately. So we'll see down that when it's a data frame, it has, let's say, underscore DF, or when it's a matrix, it's MET, or when we are using it, something is saying, okay, addition, so ADD underscore mat. So it's always good to have names that are explanatory. So these were some of the functions that sirs talked about in the lectures. I will not be explaining them again. However, I would specifically like to look at this log function. So like we were talking about, it can have multiple inputs or multiple arguments. So what does it mean? So I'll just put a question mark and log with this and press enter. So here you can see this is the command we are talking about, right? So by default, so it has two arguments, x, that is the value of which we want to calculate the log, and the base. So base here is e. So it's natural log. But if you want to change, so let's just say log, I want to calculate log of 10. And if I don't specify anything, it takes the default value. So just to specify, x here is a mandatory argument. You cannot run it without the value because it would return nothing. But on the other hand, base, you really don't need to specify. If you don't specify, it takes the default, which is e. But if you specify, it can take whatever you specify. So base is equal to, let's say, 2. So log 10, 2.3, and log 10 and base 2, that's going to be 3.3. Now here you see we have used the is equal to sign. Here, the assign symbol will not work. Let's say if I try putting the assignment symbol here, let's see what happens. Oh, it worked. But in a lot of cases, it's not recommended because it does not form a part of the syntax. All right, so it's always preferred that whenever you are specifying variables, it's a good practice to use the assignment symbol. And when it's inside functions, it's good to use the is equal to sign, because as we progress over through this course, there'll be more complex functions and which would not be able to use the assignment symbol inside it. All right. So moving on from the arithmetic operators, we go into relational operators. So greater than, less than, greater than equal to, less than equal to, is equal to, and not equal to. So these are all self-explanatory except this one. So here you see for is equal to, we are using a double is equal to sign, right? Because a single is equal to is used for assignment, right? While a double is equal to is to check for equivalence. All right. So if you remember, I can just write x, y, and z, 5, 12, and 12. So if I just run one of these, what do you think? Should it come true or false? This one. Y greater than or equal to z. True. All right. So yes, if I run this, its output is true. So the output of relational operators is true or false. You might have heard the name Boolean. So let's say I want to write what we just discussed. So I'll put a hash here and say that output of relational operators is true or false. It's always recommended to use them in capitals. Or you can simply use capital T and capital F. They mean the same. Okay, now logical operators. So when you say logical operators, you are actually combining two or more relational operators. So one side is this, there's one more side, and you want to see all or none sort of a case with this. And it's not restricted to just two comparisons. So here for simplicity, I've shown two, but we can also increase. So in one of you, tell me what is the output of this. X is less than Y, so it's true. Y is equal to Z, that is also true. So if we do OR, so true or true. So we know how the AND, OR, and NOT gates work, right? You might have learned about them in school. So for an AND gate, all the conditions need to be true for it to be true. For OR, at least one condition needs to be true. And NOT gives you the opposite of the condition. So let's say, let's try and execute this one. So X less than Y, this is true. Y is equal to Z is also true. And will give you true. And now this one. Anybody? What do you think this is going to be? So such are going to be questions in your exam also. So in your final exam, the final assessment that you would have in March, you would not have access to RStudio, but based on what we have learned and what you think is going to be the working inside, Such questions are going to be asked. So you have the values of X, Y, and Z. Here you can just compare and think of what the output would be. So if nobody wants to answer, no problem. So
False.
since one is, yeah. Anybody? Yeah, the output is going to be false because one of them is false here. So let's say I've typed the whole thing, but I just want to execute this part. I don't want to type it again. So I can just select this and press Control Enter. So I'm only sort of executing this selected bit. So we can see here. So let's say X not equal to Y. This is true. So when I negate this, it's going to be false. It's just the same way of saying X equal to true. X equal to Y, right? So, all right. So we come to the end of our lecture number 2. Let's move on to lecture number 3. By the way, just to clarify how we have these things here, this arrows that we can expand and compress. So when you add these 4 lines here, 1, 2, 3, 4, you see this arrow coming up. So it's just it sort of divides your script into chunks. So it's easier to work with when you have multiple independent pieces in your code. You can also make different scripts, or you can have them all in the same script, but just separated for better working. All right. So in the next week, previous one, we talked about a single value to each variable, but now let's say we want to increase. How is the negation useful practically? Okay, so let's say I'll give you an example which I recently used in one of my codes. So I want let's say it's easier for me to say the length. Okay, let me think of an example. So let's say you have 2 different, so I'll give you the answer in just a while. I'll just clarify these multiple variable assignment, and then I'll come back to your question and give you an example. Okay. So here we are talking about multiple values. So let's say if I run this here, yeah, so I'm running it. So it's sort of overwriting these variables. So yes, again, whenever you're overwriting variables, whenever a variable is already here and you're assigning a new value, be careful that you may not be able to get the original variable back. So this is just when you start working, you need to be mindful of that. Okay. But here in this case, I don't want my original value. So I'm fine with overwriting it. So when I say X from -10, so the colon symbol is sort of 2, TO. So it's -10 to 20. And this goes on through integers. So it keeps adding 1, 1, 1. So when I run this, it's going to give me from -10 until 20. So there are going to be 31 values in all. Another way to make this list is to use the sequence function. Again, you can see SEQ is followed by a round bracket. It means it's a command, it's a function. And I want to actually see what are the exact arguments here. So I'll again use question mark, seek bracket. So it says that the first argument is from, the second argument is to, and by is sort of the break or the interval. So these are, in a way, they are positional arguments. So the first, so even though we have not written from is equal to 4, 2 is equal to 9, by is equal to 1.5, the output is still going to be the same because these are positional. Sometimes when you have a lot of arguments, it's always better to have the name of the argument is equal to and the value, so that there's no confusion. So here it's going to give me 4 and then adding 1.5 to it. So that'll be 5.5 and then 7 and then 8.5. And then it won't go beyond because it is greater than 9. Z and A and then B. So yeah, so here when we use C, this is when you don't really have a pattern in your list. I just have some random numbers, right? Or I have characters. So whenever I have characters, I will always have each of these characters in double quotes. Now, so coming to the question that you asked about when would negation be important? Let's say I want to compare these 2 lists, A and Z. or rather B and Z. Okay, these are all character lists. So I want to find, so there's a function which can sort of give you the intersect of the two lists. All right, it's I won't go into that at the moment, but let's say there's a function which tells you the intersect. Now I want to find the elements which are not a part of the intersect. There is no direct function for non-intersection. So what I do is I do intersect and then I put a exclamation mark. So it will give me the elements. Let's say I want to say elements in Z, not in B. So I find the intersection and then I said not, right? I hope that gives you an idea of where negation can be used. Let me know if I need to clarify again. All right, good. So now I want you to look at lists A and B. So they both have 3 elements, 1, 7, and 10. So, all right, most welcome. Yeah, so both lists A and B have 3 elements, but now you can see here one of them is a number type list, and one of them is a character type list, right? So R will not be able to identify numbers just because they are numbers. It's 1 and it's 7. If they are in double quotes, it will treat it like characters. So you cannot actually perform any mathematical operations on a list which has numbers, but which are character type intrinsically. So this is something we need to be sort of mindful of. So how do we, let's say if it's not possible for us to look here, there's another way to check that. So one of them is str or structure. So we write str. And another thing about RStudio is whenever you type 3 alphabets, it is able to give you suggestions on everything that matches those 3 alphabets. So I typed str, it's given me all these options. So I just want the first one. So here, so I write str, and within that, let me write P. So it gives me character, 3 elements and the elements, right? So now we'll also use str when we further move on to tables, matrices, data frames, and all. Okay, so now a lot of times you may not want to work with the entire list. You will only be working with a part of it. So we want to extract one or more elements from the list. Now a list, as it's synonymous to a vector, it is one dimensional. So it just has elements one after the other. There's no 2D in it. Here, it does not make a difference whether it is a column vector or a row vector because it's 1D. But the elements, they start from 1 onwards. There are some other programming languages where indices start from 0, but you can forget them for the purpose of this course. For R, it starts from 1. So let's say if I write X and 3, it's going to give me the third element. The first element was -10, -9, and then -8. So yes, it gives me -8. And then Z, 4 and 5. So it gives me my name, right? Now we want to move on to something known as data frames. This is just one-dimensional list. If you have any confusion about lists, you can ask that now. If there are no doubts, I'll move on to data frames. So one of the things in data frames is I believe most of you would have worked on Excel, right? So what you see in Excel is it's a data frame. And because many a times, each of the columns that you look at, they don't have the same data type. Some of them can be numbers, some of them can be names. As a very simple example is, let's say it's a school or a college attendance list. So you have roll numbers, some of the roll numbers can be just numbers, somewhere places it's alphanumeric. Let's say it's your name, your class, and your mobile number. So one column is character type, one column is number type, integers. If there are some marks, they can be decimals. So they're just different types. Right. So when each column is a different type, it's known as a data frame. So instead of, so you can of course read an Excel file into R. However, R has a slight difficulty to work with Excel file, that is .xlxs extension is not readable into R very efficiently. So that, which is why you would have seen that .csv or .tsv or .txt files are preferred. So they are nothing but these tab separated. Tab means what you press right, which is right above caps lock. So it adds a space of about 4 or 8 characters between columns. And CSV, it's a comma separated file. So each element in a row is separated by a comma. So you can, so let's say you have an Excel file that you want to read into R Studio. So in this file and save as menu, you can save it as .csv, and that's going to be simpler. So for today, although I'm not working with an Excel file, so let's say I have this, so this data um, command here, I'll just enter that. So it gives me a list of different data frames that are available in R by default. So when you have installed R and R Studio, this comes by default. So it's good to work with. They may not be of use if for your work, but to understand R, they are really nice. Okay. So yeah, so just to say, you can minimize and maximize from here, right, in case any of your panes go missing. So for the purpose of today's session, I will be starting with the CO2. So you can see that CO2, this whatever type of data it is not available here. It is available there. So since I want to use it for today's session, I'll just assign it to a variable that I would call CO2_TF. It's your choice how you want to name your variables. Some people prefer dot, some people prefer underscore. It's completely up to you. Another thing is that R is case sensitive. Okay, so if I have a variable capital C capital O2_TF, it will be different than this. So just to show, let's say you can see there's already a small z here. Let's say as I write capital Z is equal to 5 and I run that. So you can see this comes up. So just be careful of caps lock being on and off. So all right, so for the CO2 data to be visible in my global environment, I will use this assignment function here and it appears. So now I can actually take a look at this and you can see here values have a different section and data has a different section here. So it's just to sort of give some grouping so you can better work with your data. So you can see here what this data has. It has 5 columns: plant, type, treatment, some concentration, and the uptake. All right. So I will not be going into what exactly the data frame is all about, but there are a few commands that were discussed in the lectures. So structure, we already saw what structure does. So I'll just copy this and I'll paste it here and run it. So initially when we use structure, it showed us that it was a list, it was a character type, 3 elements, and these were the elements. Now, when I did structure for this data frame, what you can mainly focus on is 84 observations of 5 variables that we saw. Dollar indicates columns. So if the first column is plant, next column is type, treatment, concentration, uptake. The rest of it here can be ignored for the time being. These are something that we would not be dealing with and they don't hamper our working for the day. Class is a very similar sort of function. So what it gives us is something that you saw here also. Grouped data and data frame. So let's just focus on data frame for the time being. So as we discussed, it's a data frame. Dim is for dimensions. So what do you think the output of dim is going to be? It gives the dimensions of the input. The input is CO2_data frame. Anybody? 3 rows and columns, yes. So dimensions gives you the exact number of rows and columns. Now, can you tell me what dim would give? You have a hint here. 84 observations of 5 variables. 1 into 3. Why do you say 1 into 3? So just mentioning, wait, this is CO2. CO2. So this is what the data frame is, not the list. I want to find the dimensions of this thing. The CO2_DF. Any idea what the dimensions of this thing is? So it's a table, right? A data frame is just a table, right? So you specify the number of rows and the number of columns, right? So it should be 84 by 5. And what happened? Yeah. So it does not give that cross symbol in between. It just gives you a list. Now, if you can look here, it's a list. It's a list of 2 values. The first value is the number of rows. The second value is the number of columns. Now, if I can just give you a quick question. Let's say I store this somewhere. I store it in the variable len. Okay. So you can see len comes here. If I now want to find the structure of len, what would it be? When you have 2 values, one after the other, what is the data type? We just saw this a while back. What is the structure of the output of dimensions? One value is 84, second value is 5. So what's the structure of this? It's a trick question, if you can answer. Data frame. So no, not data frame. Think about it. List, that's right. So we have 2 values, one after the other. It's a single dimension with 2 elements. So the structure is this sort of, so if I just write class of len, so it's integer type list that you can understand from the square bracket here. As we just discussed, square brackets indicate length, or rather that it has more than one element, right? So where were we? Okay. So dimension gives you an output, which is a list, where the first element of the list is the number of rows and the second element of the list is the number of columns. So if you think about it, what we basically wrote here was structure of dimension of CO2 TF. So this is like a nested command, right? So just like you have it in board mass, the bracket inside is solved first. So first we see the output of this. This output is fed into structure. So if I run it all together, we'll again get the same thing. This is something you would see very often in the coming lectures. Okay. So just familiarize yourself. And the best part about using RStudio is if I have my cursor here at this bracket, you can see that this one is highlighted. So I know that, okay, I have a closing bracket, I have an opening bracket corresponding to it. And if I press it here, this is my closing bracket, this is my opening bracket. Number of brackets that open should be equal to the number of brackets that close. Let's say I miss this bracket. So what happens here? I get a cross because it is not able to make sense. So I need to put the bracket back and the cross goes. Okay. Now there were a few more things. Read.table, read.csv. I do not have a CSV file with me right now that we can use. However, I would like to show you the difference in when we do a question mark of read.csv. Let me use read.table first. So if I write read.table, what it says is that you need to specify the name of the file. This goes in double quotes because it's a character. Then we specify whether there's a header or not. And the separator you see here. So here the separator is blank. So you need to specify a separator. Separator means how is one column separated from the other? Is it separated by a tab? Is it separated by a comma? Is it separated by a space? Is it separated by a semicolon? It could be anything. Is it even separated by sort of, let's say, every A you want to separate? Okay. So on the other hand, when you see read.csv, the separator by default is a comma. So when you are doing read.csv, you don't need to specify the separator here. You can just directly go for file and the header. Now, just give me a minute to see if I actually have a file here. Okay, I don't, but I can maybe download one of these files. Okay. I'll just quickly show you this. So let's say I have the CSV file here. Okay. Download this. In the meantime, if you have any questions, you can ask. Okay, it's going to be in the RAR file. Wait, we'll come to it a little later. But I hope you've understood how read.table and read.csv commands differ. Okay. Yeah. Okay. Is there a function to create a random data set? Could you elaborate? You would like to generate random numbers or what? You can create a random data set. I am not aware if you can create a random data set in R. I'll have to check. So I will check and let you know. But I believe there are a lot of data sets already available within R. So you can just, like we saw here, you can take a look at each of these and maybe you can select one of these for any type of, you can just try random commands and work around with these data sets. I think that should help you in whatever you want to achieve using the random data set. But I'll anyway check and let you know. Okay, so moving forward, so just like we saw here, here it's 84 rows and 5 columns. But very often, especially when you talk about gene, like let's say RNA sequencing has been done, and you have information about 30,000 genes. So here you're going to have 30,000 rows. And let's say there was different people or different samples and there were 50. So the table becomes huge, right? And it's so big that you cannot open it in Excel. You cannot even visualize it like this in R. It's going to hang your system. So we just want to get an idea of what our data looks like. So what we can do is use head and the name, let's say CO2 or DF, and it shows you the first 6 rows and all the columns. Let's say I don't want to see 6 rows, but I want to see 10 rows. So the second argument here is n is equal to 10. And it gives me 10 rows, all the columns. Likewise, if I want to see the last few rows, so I'll write tail, name of the data frame, comma, n is equal to, let's say 3. I just see the last 3. And this gives me a fair idea of what my data set looks like. So I don't need to visualize the whole thing. There are 3 functions: names, row names, call names. So as you can see here, this right here is a row name. In most of the data sets, row names are going to be indices. But it is very often that row names can also be some important name associated with each entry. Nevertheless, if I write CO2 underscore DF here, I'll get all the row names. Now you can see here, these are actually character type. They're names, but that does not matter. So likewise, if I write call names, what would I get? The column names, all right? So if I run this, these are the 5 column names. And if I just write names, again, I get the same thing because a data frame is defined by its columns. And we will see why that is so. When we create a data frame, this is when we used an inbuilt data frame, but if we create a data frame, it's generally created using the columns. Nrow and ncol, they give you the number of rows in column, which is same as the first and second values of dimension output. So dim bracket your data frame, it's the same thing. Now, just like we saw for lists, when we want to extract a particular element, you just write the name of the element in square brackets. In case of a data frame, now we have 2 dimensions. So when you have a square bracket, you have a comma in between within that square bracket. Anything before the comma is about rows. Anything after the comma is about columns. It's always row into columns. If you remember from the matrix that we discussed in week 2, M into N matrix. It's always row into column. So if I write here, you don't need to tell me the output. Just tell me whether it's giving, if it's going to give me rows or columns, and how many rows and how many columns would the output have. Remember, the data frame has 84 rows and 5 columns. So what do you think this gives? First 2 rows, incorrect. This only gives me row number 2. I'm not saying, this is only giving me the index. So row at index 2, right? Instead, if I would have written 1, 2, then it would have given me both the rows, right? But if I just write 2, it's going to give me just 1 row, but all the columns. All right. Likewise, if I write this 45 to 50, how many rows, how many columns will I get? Type your answers or unmute yourself and speak. So here you can see that it's just specified before the comma. If there's any confusion, if you're not understanding, please let me know. If you don't ask, I will assume that you're understanding everything. Okay. This is this is specifically arranged so that you can ask your doubts. All right. So 45, 46, 47, 48, 49, 50. 6 rows and all the columns. Right? So you can see here, it's 6 rows, all the columns. Just remember, what is there before the comma is rows. It's a constraint on rows, and whatever is there after the comma, it's a constraint on columns. Now this, just first try and see this comma right here. Okay, this is a comma. After the comma, it's blank. So we're talking about all the columns here. Before the comma, there's a list. C bracket 10, 16, 49, 80. So here what I'm doing is specifying rows. I only want row number 10, row number 16, row number 49, and row number 80. So if I run this, I get just 4 rows and all the columns. Now, another way to put a constraint on rows is using the subset function. So this is a slightly difficult, so I'll show it to you slowly. So let me type it again. So what I do is I write subset, and it's a function, so I put a curved bracket. Then I want to subset. So you can see here it says X. So here it means what do I really want to subset? So I want to subset CO2 underscore data frame. All right. Now it's going to be the second argument. So I put a comma and the second argument. The second argument is my condition. So we just saw these, what were these? Relational operators, logical operators. I don't remember what they're called. What are they called? This one that we saw here, relational operators, right? So here I'm putting a constraint using relational operators. So relational operators, I'll put it on a column. So let's say I only want to subset or filter observations where concentration, whatever the concentration, I think it's CO2 concentrations are greater than or equal to 400. So I write conc greater than equal to 400. So it's going to give me all the rows where this column here is greater than 400. So you see here, I have got some lot of outputs. It's a long list, but this is the list where the 4th column is 400 or above. All right. I can also put constraints on 2 or more columns. So I say concentration should be greater than 400. And remember we had used and. So only return rows where this condition and this condition are both true. So you can see right now there's something from Quebec, there's something from Mississippi. So when I run this, oh wait, sorry. Did I miss it? Yeah. So let me just run this here. Yeah. You can see here now everything is from Quebec and the concentration is 400 or above. With me till here? Now these are actually big data frames. So I would like to save them somewhere. So I've just saved them. One I'm calling underscore sub, the other I'm calling sub 2. Okay, I'm just running them. So we can see here that when I put a constraint of 400, I got 36 out of 84 observations. And when I put 2 constraints, I got fewer. Of course, I'll get fewer observations. All right. Now, here we were mostly talking about rows and putting constraints on rows. Now we shift to columns. So to get just one column, you saw when we were using the structure command, we saw that all the columns are preceded by this dollar sign, right? So here also when we use a dollar sign, so we get the whole column. And what's the best part about using dollar sign is, let's say I have this. Now I press dollar. So it already shows me all the columns. So it's good. So because let's say I don't remember if treatment started with a capital T or a small t, or let's say it's some complicated spelling. So I don't need to worry about it. When you're using RStudio, you can just see and then you can press enter. All right. Now, likewise, can you tell me what column are we selecting here? When it's comma 2, which column are we looking at, or which columns are we looking at? We have an answer. All rows and the second column. Perfect. And with this one, 2:4. I would like the others to answer as well, because if one answers, I'm going to assume everybody understands. But if you have any confusion, please ask. We can always revisit these concepts. Okay. So when I write, right, so we get 3 columns, and specifically we get column number 2, 3, and 4. Good. All right. And likewise, when I write C 3, 5, which columns is it going to be me? Is it going to be 3 to 5? Is it going to be 3 and 5 only? All rows and column number 3 and 5. Very good. Third row and fifth column, no. So, okay. So you can see 1 comma here and you can see another comma here, right? So when I was writing this code, I wrote it something like this. CO2 underscore df. Then I put this and then I put a comma. Now here I'll talk about rows. Here I'm going to talk about columns. Now here I wrote C bracket 3, 5. So this is about column, and this, which is blank, this thing is talking about rows. So I've only put a constraint on columns. On the other hand, what you suggested, third row and fifth column, it would look something like this. Now, what do you think third row and fifth column means? What's going to be the dimension of the output? 3, 5 on a data frame. It's something very similar to what we used to write A, I, J in matrices. That's an element, right? It's an element. So if I execute this, I'm just going to get a single value. So it's the element. So if I open it here, third row, fifth column, 34.8. That's what I got. So when you want to pick a particular element, we have to put constraints on both row and column. All right. Okay. Now, okay. So now we made these 2 files, right? Underscore sub and underscore sub 2. So I want to save these files. So let's just work with, I think sub is what I'm doing, not sub2. So I'll just write.csv. So the way write.csv works is write.csv. It's always a good practice to do this question mark file name, command name, to be sure of what you're specifying. So the first argument is your variable. So here my variable was this co2 underscore df underscore sub2. And the second argument is file name. What file name do I want to save it with? So this should always have the extension. In this case, I am writing a CSV file, so I'm putting the extension .csv. This is something you need to be careful, right? So here I'll add a comment that if writing a CSV file, the extension should be .csv, right? Using CSV. Now this just clarifies everything what I want to show here. Okay, so so I have saved this, so it should be visible here. So yeah, so I can actually see this here. So let me open it with Excel. Oh, it opens. Now I see there's this weird column that is not of my interest. I'm not interested in knowing that the original fifth row. So you remember, right? We had 84 observations. We filtered and we got some 36 we got some 36 of them. So we got the fifth row from the original data frame. We got the sixth and seventh, and then we directly got the 12th. This information, if you need, you should save this. But in my case, I don't need this information. For that matter, even if I would have saved the original thing, 1, 2, 3, 4, I don't need this because this is not adding any information. So this is row names, right? So I actually don't want to save row names. So you can see here, there's an argument which says row names. Now by default, this is true. The value the value on the right hand side of the is equal to what you see here is the default value. By default, it's true. So if I want to change it, I need to write it down. So I'll write row.names is equal to F or row.name is equal to false. So when I write this, since I have the same name here, it's going to override the file. Oh, I did not have the same name. It's trial 2. Okay. So I created a new file. Now let me open it and let's see. Oh, now we don't have that anymore. This makes sense, right? Okay. Now, let me again. So let's read this again. So we have this, we save this file 36 into 5 observations. Let's read it again. So just to read the file, you need to give the name and this. So let's read it. So now you can see again, it's 36 observations of 5 variables. Now let me open this. It looks identical, right? If I open this and if I open this one, they look pretty much identical except the row names, which is not important at the moment. So they look same, right? Do you all agree they look same? Do they look same? They look same, right? Okay, let's try this. So if I write, where is it? This one, I write the structure. So you see it's a data frame, 36 observations, 5 variables. Now, after every column, there's some information about that column. It says it's an ordered factor, it's a factor, number. So I'll come to what a factor is, but you can see this is the type of values that are there in that column, right? This was the original one that we took from the available data sets. Now let me write the structure of what we had here. We have, what was the name? Trial, yes, this one. Do you see a difference? Right? It's the dimensions are same, the values are same, but the data type has changed. The first 3, they are taken as characters. The next one was a number that's taken as an integer. The last one stays a number. So here R has sort of thought about it. It thought, okay, this looks like numbers. Numbers means non-integer numbers. So it's a number. Okay. The fourth column here, it has integers. So I'll just call it int, int. The other ones, these are just characters, right? So I'll just call them CHR, character. On the other hand, when the person actually made these files, they wanted to work with it. So they said it's only going to be either Quebec or Mississippi. There's just two options possible. So I want to call it factor. So factor is sort of the same thing as repeating multiple times. So these are the only possible options. Right here, it's a factor with two levels. It could be either chilled or non-chilled. These are just levels, rather, if you want to say. So there are certain things I could have performed on this data set, but when I saved it and when I reread it, I cannot. So we would not go very deep into what are the other ways so that you can actually retain this capacity, this sort of data type. But what we will try to do is, let me add it here. I think I have somewhere later. So what I do is, I want to change the data type of one of the characters. Please follow with me. If there's any confusion at any point, let me know. Okay, so let's pick treatment. Okay, I want to change the data type of treatment from character type to factor type. Okay, did you understand what I want to achieve here? Yeah, all right, good. So I want to change the data type. So what I'll do is, I'll write trial. I want to pick a column. So I'll write dollar, and here I pick treatment. So what I'll do is I want to apply a function on this. So the function that I want to apply is as dot factor. And whenever I want to apply a function, I'll just enclose the input in a round bracket, right? So as dot factor. So if I execute this, you can see, so before that, if I would have just executed this one as we saw previously, it's just going to give me chilled, non-chilled in double quotes. Nothing fancy about it. But when I did it after as dot factor, it gave me those values, but it also said something like levels, chilled and non-chilled. Now I want to save this output back into this column. So I'm going to overwrite a column because it's the same information. The values are the same. It's just the data type is different. So what I'll do is I'll write trial. What was it? Trial CO2 dollar treatment, and I will put the assign symbol and this. So we'll read it from the right. I had this originally. I changed it to a factor, and I want to save it back to the same column. So I have not run this line as of now. So again, str of trial. Before I made this change, it looks like this. Character, 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 int number. Now I run this, and I want to see the structure again. Do you see this difference here? Treatment, treatment, right? So these things, so I'll just introduce a term to you. This is something which is known as data wrangling. So we did not change anything about the data frame. It had 36 observations of 5 variables. We still have 36 observations of 5 variables. But making it a factor gives it some more usage. We can use it somewhere else. It just increases the, I don't know, efficacy. So we've done that. So we're not changing much. It's just left and right here and there. That's data wrangling. Okay, with me till here? Sir also introduced one more thing. So when you want to read a CSV file, not from your local system, you can give, so inside you want to give this. So it's a nested command. Inside read.csv, you have URL, and URL itself is a function which gives, which takes the URL or the location in double quotes. All right. So for this thing, we need internet, right? Because we are using it from the internet. So this requires internet connection. Also, this step will be slightly slower. I'll just try and run this. So you can see it's running. Oh, it went fast. So let me just run it again, and you observe what happens here. Okay, right next to this broom here. I'll run it. And you see, there was this, for a little while, there was this red hexagon or octagon. It just said stop. So in case you run a command and you don't want it to run completely, you can press the stop and it terminates that command. All right, anyway. So fine, this was the same iris data set that Sir was working with. Okay, so now we had this CO2 DF, the original file, 84 into 5 observations. If I write call names here, this is what I get. Now, what's been bothering me is that conc and uptake do not start with a capital letter. Okay, it's just difficult to work with. I mean, I'll have to remember. So call names gives this output. I can use the same command to change the column name also, right? So if I write call name, the data frame's name, I get all of this. Now look at this, just the left side. What is the output of this thing? Call names and 4. So call names gives us a list, right? We just saw. It's a list of 5 elements. If I write call names in square bracket, I write 4. What would it give me? If I execute just the left side, what I've highlighted here, if I execute this, what would I get? Anybody? Right? Correct. So I'd get conc. Now I just want to change it from small conc to capital, right? I would not get the 4th column. I would get the name of the 4th column. So you think of it like this followed by the output, 4th column name, right? So if I run these two and I again check the call names, you can see from this, it's been changed to this. The others are as it is, but I changed the 4th one from small to capital and the 5th one also from small to capital. Okay, so this brings us to the end of lecture number 3. And all right, now lecture 4. So we want to make a data frame. So like I said, data frame is defined by its columns. So these 4 right here, these are lists. Okay, first list. So I can clear this old, I think I can just clear these objects. So you can see this broom here. It'll clear everything from here. The environment is empty. I can also clear this if I want, but anyway, let it be. So I have these 4 lists with me. So I'll just execute them quickly. Ages, system, systolic, diastolic, and I've just added a column, gender. So length, it gives us the length. Now, generally, these commands make sense for a column or a list. So if I write length of, I can directly write ages, or I can write, yeah, if I write ages, that's fine. What happened here? Okay, I think, anyway, I can just use this one here. So I'll just make a data frame with these 4. So I'm just specifying data frame, and these are the 4 lists which make the respective columns. First column ages, then systolic pressure, diastolic pressure, and the gender. So I run this, I get the patient data. This is exactly the same as our lists. So here I wrote length, right? What I can also write is length of patient data, $ages. That would also give me the same thing, right? Now, can anyone think what would be the output of this? Length when I just write patient data. Hint is that a data frame is defined by its columns, not the rows. Anything? Any idea? Any guess? It's going to give me 4. It gives me the number of columns that are there. So it's not a lot of use, because I would have rather preferred using n col, number of column and number of rows respectively. But nevertheless, it's just for your information. Min, max, median, mean, variance, standard deviation, these are exactly the same as were discussed in the lecture. So I will not be explaining it at the moment. So yeah, so let's see if I write summary of the patient data here, it gives me this. So for the ages column, it's giving me all these parameters. For systolic, diastolic pressure, also it gives me everything. For gender, it's not able to give me any information. I would have liked to know, as one of you asked in the discussion forum, that how many are M, how many are F, but it doesn't give me. So what I can do instead is, does this look familiar to what we just did? So we have the data frame. We take one of its columns here, gender. We convert it to a factor. So R is able to identify unique values. It says, okay, I found a unique value M. I found another unique value F. That's all. So I'll just specify one of them as factor 1, factor 2, and I just reassign it to the same column. So when I run this, and when I want to again find the summary, the 3 columns stay the same, but now this column, you see, it changes. It's able to give me that, okay, there were, in the patient data, there were 6 females and 4 males. So this is sometimes, this is, one of the cases where converting it to a factor may be useful. And of course, you can convert it back to character, right? So I might not be able to show it in case, let me just be mindful of the time here. So, but again, you can take this, now it's a factor, you can again convert it to a character, and it returns to its original form. All right. So quickly moving on to some plots here. So it's good to imagine any numeric data. It's good to view it in one or more ways. So one of the common things is a histogram. So histogram, if you again take a look at, if you do question mark hist, we'll just see that it needs X, which is basically a vector of values. So what do you want to plot? So if you remember histogram, if when you would have plotted histogram back in school, so what it does is, what you would have wanted to do is make bins, right? So maybe I'm making bins of 5 or 10, 5, 10, 10 to 15, and I'm counting the number of values that fall within each bin. So that is done by default, that is done intrinsically by this function. So if I want to find the histogram of age, I'll just run this, and it's still running, as you can see here, and it plots. I did not specify any x-axis label or a y-axis label or the title, so it's just giving me what I specified. So this directly becomes here and as well as here. So again, of course, you would not find such images anywhere. So there are ways, as you can see here, you can find something like xlab, ylab, main means the title. So these things you may want to write, you may want to change the colors, you may want to add some lines. So this would be more explored in the next week's lectures. So until then, it's a simple histogram. Okay, so week 4 also finishes. Oh, sorry, lecture 4 also finishes. Now lecture 5. Okay, here is just an example of another data frame. Let's make a data frame. So I have 2 lists, CTRL and TRT, which imply control and treatment. So this is just a different form of the plant data, that plant growth data set that sir discussed. I'll tell you what I've done different in this. So, okay, so we are making a data frame. We are specifying the name of the first column, of the second column, right? So we run this and we get this plant exptdf. Okay. So now I actually want to find if the treatment has actually done any difference to the growth of the plant, right? Whether it's this length or whether it's the dry weight, whatever it is, I want to find. So we want to do a t-test. So the underlying assumptions is that the data should be normally distributed, and there should be the variances of both are the data 1 and data 2 should be equal, and both the samples should have the same number. So to find the same number, you can already see from this that so a data frame, by the way, can only be made when the number of rows. So when you say there are 10 rows and 5 columns, it means each column has 10 observations, right? So we've been able to make a data frame. It means that both these have the same length, but of course we can also check using the length argument. Length CTRL, that's 10, and length TRT, also 10. Are you with me till here? Or should I go slow? All right, good. I hope the others are also equally with me, because I am getting answers from only a few people. You can stop me anytime and we can redo some of these things, okay? So like was shown in the example, we do a Shapiro test to find out if the data is normally distributed or not. Now, for a Shapiro test, the null hypothesis is that the data is normally distributed, and the p-value here, it is greater than any threshold you would set. It's a significantly high, I mean, it's the p-value is greater than 0.01 or 0.05. That's normally set as a threshold. So we cannot reject the null hypothesis. So we accept the null hypothesis, which means that it is normally distributed. Likewise, we do for the other one that also say, yes, they are both normally distributed. So this argument is satisfied. Now we want to check equal variance. So there's this function called var.test. Here we specify the two together. We run this. Again, the p-value here is very high. So it means that we cannot reject the null hypothesis. Here it says the alternate hypothesis is not equal to 1. Therefore, null hypothesis is that the ratio is equal to 1, and we cannot reject the null hypothesis. So we accept it. All right. And now, have you heard about paired and unpaired t-tests? If any one of you have heard, can you quickly tell me what it means? No? Okay. So you can see that there are 10 observations, right? If I open this, there are 10 observations. But it does not mean that the same plant, when like the same exact one single plant when grown in the control conditions versus when grown in the treatment condition. It does not mean that, right? So I could have changed the order of control and I could have changed the order of treatment, and still my data would mean the same. So observation 1 from control and observation 1 from treatment, they're not corresponding to each other. So it means that it's not paired. Left and right are not paired. So by default, the t-test is unpaired. We would not be going through whether there's paired t-test or not. But what I would like to show you here is, if I write this, so by default, you can see that it assumes that it's not a paired data. So if it's a paired data, in any case, we can specify that. So anyway, so t-test takes X, it takes Y, and we specify that variance is equal because we just saw it. So we have just specified why we are doing an unpaired t-test, and we run this, and we see the p-value, right? The p-value is very small. We can reject the null hypothesis, and we accept the alternate hypothesis. That means there is a true difference. So whatever treatment was done on these plants, it actually has an effect. So let's just visualize it. So whenever you have two or more different data sets that are sort of distributed, you can make a box plot. So I'll run this, and let me just expand this for clarity. Can you see this? So what did I specify? I specified the first argument, which is my actual data. And my data here looks like this. The first column is control, which is plotted here. The second column is treatment, which is plotted here. Right? It takes columns. Box plot takes each column, plots each column. I wanted to specify the Y-lab, otherwise it would have given a random name. So it's height of plants. And names here are actually the X variable, X labels. So I specified I had two. So I specified them within C. C, the first one, control, comma, the second one, treatment. Any confusion? Nothing? Okay. So somebody mentioned that, yes, the box plot, actually this bold line that you see here is median, but when we are doing a t-test, we are talking about mean. That is true. It is not the exact same thing, but it is the best visualization tool that we have. Okay, so you would see box plots being preferred everywhere whenever there's whenever you want to talk about these different, you want to talk about differences in samples. Okay, now we just saw that this was one way to write it. Any question? Nothing? Okay. So there is this plant growth data set already inbuilt R, right? So if I just save this here, right, you see plant growth year 1. So you see it's very similar, right? There is a control data set, there's a treatment data set, there's a treatment 2 data set, and there are corresponding values. Right? And let me run this again. And let me open this alongside. I'll just close these. So you see this one that we had already in R. And this is the same thing which I made. Same values, control treatment 1, treatment 2. But they are in different columns, right? So the exact same data, as far as I know, this is known as the short form. And this is like a long form, quite literally. So both of them have the same data. So if I ask you, which one do you prefer? I mean, like, it's like both things have the same information. So why should there be a question of preference? Now let me write. So this summary command that we used. So first we do it in this long form thing. So we do summary, and what it does is so the first column is weight, the second column is group. It says, okay, the average, I mean, mean, median, minimum, maximum weight is this, and there are 3 groups with 10 observations each. But now actually the mean, median, they're not right, okay, because 10 values, they come up from control, 10 come up from control treatment 1, treatment 2. So there's no point if I want to find the average of this or the median of this. It is sort of giving me no useful information. On the other hand, if I write summary from the short form, where each of these 3 are a different column, I get this. This is more meaningful. So there would be different cases, there would be different times when a certain command better works with the long form or the short form. So in this case, the summary works better with the short form, but it's not necessary. Okay. So this is again another example of data wrangling where you just want to change one form to the other. Here I specified it one by one. However, this is not the right way. There is another function which is known as melt that you would come across in the next week. So we'll revisit this then, right? It's converting from long form to short form. But I just wanted to introduce it a little. So anyway, so now plant growth 2 here, this is more suited for a few other comparisons. So what we'll do is we'll, again, just like we did with the t-test, here we have more than 2 groups. So instead of a t-test, we would like to do an ANOVA. But nevertheless, just like previously, we would find the normality. So you can see each of these data here, the p-value is greater than 0.05. So each of these 3 are normally distributed. And let's just anyway calculate the variances of the 3 groups, of the 3 comparison, control and treatment 1, control treatment 2, treatment 1 and treatment 2. So each of these things, you can see that the p-value is greater than 0.05. And now I want to make a box plot. So I want to make a box plot using both the data. So sometimes I have this sort of a data, sometimes I have this kind of data. So this is what we just saw here, right? Box plot, when you specify this, it takes each column and it makes a data frame. So, sorry, it makes a box plot. So what I'll do is, I'll just copy this here. And if I run this, you can see it's able to make it simple. If I make it a little more fancy, it's just adding these X and Y labels. But now if I want to use a long form, the input slightly varies. So you can see now I specify my data frame and I tell that weight is what I want to plot and group is my 3 rows, or rather the X. So it's Y tilde X. That's an easy way to remember. I want to plot weight on the y-axis and group on the x-axis. So I plot this. It's the same thing. I think I just added, yeah, this group thing came here, but I can remove that. All right, so you can make a box plot using either the long form or the short form. It's upon your preference. All right, so we want to find if the three data sets actually differ. So again, here we use one-way test, and it also uses the same sort of notation y tilde x. And this is my data name. Variance we saw is equal to true. So it says that the p-value here is less than. So if we would have selected 0.01 as a p-value, we would have said actually the data is not so different. But here the p-value, mostly the cutoff is 0.05, p-value less than 0.05. We can reject the null hypothesis. We can accept the alternate hypothesis and say that the data are actually different. Any more questions? Okay, we come to the last lecture. Again, about vectors and matrices. So quickly, I'll just clean the screen here. Okay. So, hello. Any question? All right. So let's say we have two more lists, A and B. Each of them have 6 elements. Number type 1 to 6, 1 to 6. Okay. So if you want to add a scalar, we just simply write vector plus the number that we want to add. Let's say I want to add 4. So 4 is going to be added to each element, right? So if I just write this, it's going to print. I'm not saving the output anywhere. I'm just writing and it's giving me the output here. So 1 to 6, they now become 5 to 10. If I want to add two vectors, of course, the important part is that the two vectors should be of the same length. So I just add. So what do you think would happen if I write another element here? Let's say I write what? Minus 40. I run it again. This gets overwritten. If I write this, it gives me a warning. What does it say? So the longer object is not a multiple of the shorter object. So sometimes it may give me an error that, well, I cannot calculate this. Sometimes what it does is, what it was element wise, right? 1 and minus 10, 2 and minus 15, 3 minus 20, 4 minus 25, 5 and minus 30, 6 and minus 35, and then it went back. So 1 and minus 40. So it gave me minus 39 as the last argument. Now I know this is incorrect. I just need to be careful. So A and B, and now if I run this, no warning and give me the right output. Scalar multiplication, multiplying all the elements by a certain number. Here I multiply them by 2. Now I want to find the dot product. So we know to find the dot product, the two lists, the two vectors should have the same length. In this case, yes, they do have the same length. So if I just write multiply, this gives me something. Can you tell me what it does? What has this thing done? This is definitely not the dot product because I know dot product's output is a scalar, a single value. So can you tell me what this is doing? We're almost at the end, just a few more commands. So don't be sleepy. We'll wrap it up by 8. So what do you think this has done? You have A and B here. So each value is multiplied. So it's a pairwise multiplication. There could be cases where this is important, but when you want to find the dot product, this is not what we want. So now dot, if I just directly, so dot product is something not that everybody who uses R will be needing. Let's say if somebody is using R for economics, they might not need to find dot product of something. So this is not available in what we call base R. Base R is what, when you downloaded, when you installed R, when you installed RStudio, what you got was base R. All these functions that we saw until now, they were in base R. You did not need any fancy package for it. But sometimes you would need fancy packages. You would need specialized packages. So there are two ways to install a package. One of the things is tools, install package. Here you write package name. right? So we could just write, so the dot product that I want, it's a command in the package geometry. So I'll just write geometry and I would press install. I actually have it installed, but let me install it here. So you can see here, it's actually writing a command, right? So what it did was it added this command install dot packages, and in double quotes, it said the name of the package. Now I actually have it. It does not matter if I download it, if I install it again, but you don't need to install it every time. And this step, of course, since you're downloading it from the internet, you can see it's trying this URL. So you of course need internet connection. Once you've installed it, you don't need it. But let's say over months that you have been using R, you keep installing multiple packages. For example, I have probably installed some 50 packages. But if I install all of them, and if every time I open RStudio, they're all going to be sort of opened alongside, it's just going to make it very slow, right? It's going to contribute to RAM, and it'll just make it sluggish. So what it does is, even though it's downloaded, it's sitting in the library. What you want to do is call that library. So after you install, let's say you installed it today. Now tomorrow, when you want to again use any function, any command from this package, you would need to do library. So I do library geometry. So what it does, now I can actually use the commands that are a part of the geometry package. So install once, but library, where you are loading the package, this needs to be done every time you're opening a new R session, each time you're opening RStudio. So now geometry has this, so just before I go there, so yeah, so if I do question mark dot, so it says this is a part of a geometry package. So I click this here and you can see this thing, right? So it says dot, it's a part of the geometry package, and it's the documentation for that. So I just give it my two vectors, and it's able to find the dot product. So you can calculate, and the output would be minus 560. We studied in one of the lectures that norm2 actually gives us the magnitude of the vector. So I'll just write norm, right? So here, 2 norm. These are some different things. So here we know that 2 gives us the value or the magnitude of the vector. So I want to find the magnitude of vector A, right? So of course you can calculate it using 1 square plus 2 squares and so on, and finding the root. And this can do it quickly. So you need to know the formula, but R can do it quicker. And let's say we want to find the unit vector. So unit vector is a vector with the same direction, but with the length reduced to 1. So we divide it by the length. So now how do we write a complicated formula like this? We write A, and we want to divide it by something. So I have one way, either I can save this and then I can simply write this and this. Or the other ways, I can specify the whole denominator in a bracket. This bracket is same as what a mathematical bracket you would use. And then I specify. So you see, we get the same output nevertheless. But this is much simpler. This looks cleaner. So it's up to you how you want to calculate, how you want to write. And again, now we want to calculate the angle between the two vector in radians. So again, you can see here, this looks very complicated. So again, let me reduce it. So what I'll do is I'll write M here, and I'll write norm of B, and it's equal to, and I calculate the norm of B here. So this is one way. The other way was, so we know cos theta is equal to the dot product divided by the magnitudes of each. So let me write the right hand side first. So the dot product, we have A comma B, and we divide it by the product of N and M. Now we want to find the inverse, cos inverse, or A cos in this case. This thing. becomes simpler, smaller, simpler to understand, but we'll get the same output nevertheless. All right. Is that clear? Okay. All right, great. So then we just quickly move to matrices. So for a matrix, matrices and data frames, they have one important difference, which is that matrices can only hold one type of data. We saw in data frame, one can be integer, one can be character, factor, etc. But a matrix can only be, let's say, a number, only numbers. So for the purpose of this today, we're only talking about integer matrices or numeric matrices. So now again, looking at the function matrix, this says data, ncol, nrow, byrow. These are the four most important arguments. So A, as we know, this was just a list. So we want to actually want to convert this list into a matrix. How many rows do we want? I want 3 rows and 2 columns. So it's going to be like a rectangular landscape form matrix. But how do I want the values? I want to be 1, 2, 3, 4, 5, 6. I want to be 1, 2, 3, 4, 5, 6. So if by row is true, they're going to be 1, 2, 3, 4, 5, 6. And if by row is false, it's going to be by column. So 1, 2, 3, 4, 5, 6. So let's just quickly run each of these so you can see. Oh, I think I mentioned wrong. Number of rows is 3. So yeah, it's a portrait form, right? But you can see this is by row 1, 2, then 3, 4, then 5, 6. And if it was by column, then it was 1, 2, 3, 4, 5, 6. Right? So it's up to you how you want to further work with the matrix. Another way to make a matrix is using C-bind and R-bind, which is column bind and row bind respectively. So again, whenever you are combining 2 columns, the number of entries should be the same, right? Or if you want to combine 2 rows, the number of entries should be the same. So if I write C bind A and B, it's just combining the 2 vectors one after the other. And in R bind, it's going to be like this. The number of values should be the same, otherwise it will throw an error. Okay. Now you can see in this case, you have some column names. In this case, you have some row names. These can be removed. So we just saw how you can remove, how you can change row names and column names. So these can be removed. Let me know if you want to try. You can give it a try and let me know if it works. Okay, I don't have these anymore. I think I removed them. But let me read those again quickly. Where did it go? So plant growth. So yeah, you can select multiple and just press Control Enter and everything works together. Okay. So we have this thing here. Right. So here we had these data frames, right? We saw 30 observations, 2 variables in the long form, and 10 observations, 3 variables in the short form. And we can also convert this to a matrix. If I do this, what do I get? I get weight and I get group as 1, 2, 3. This is not what it was, right? It was very different. But what happened was group was actually a factor here. So it just converted it to so it just converted it to these respective 1, 2, 3. And also we know that matrices cannot have 2 different types of data, right? Here it was number, here it was character. So here converting to a matrix did not make sense. On the other hand, here we can actually convert it to a matrix, right? Because they're all numbers. So if I write this looks very similar. It looks very similar and we can do similar things. However, there is one difference. So let's say I save it in a variable named temp, right? So temp here, this and this, they look almost identical, right? They look identical. If I don't write the structure, they are the same. But there is one small difference. So if I write plant underscore growth 2 and I write $sign, I get these 3 options, right? I can select one of them. On the other hand, if I write temp and I press a $sign, there's nothing. There are the same columns here, but $sign does not return any column. So if I forcefully write TRT, what would it say? It says error. So this operator, this $sign, is invalid for such a kind of so for a matrix, even though it has a column name, you cannot use the dollar symbol for it, right? So again, this is just for your information. You don't need to remember all of these things. So yeah, so likewise, we made these two matrices, M and N. So here you can see 1, 2, 3, 4, 5, 6. This is the other one from the B vector that we made. So both of these are, so what would you call them? 2 by 3 or 3 by 2 matrices? If I do dim on any one of these, what would I get? 2 by 3. Good. Very good. Very, very nice. Okay. So simple things, transpose. So transpose is nothing but T. So now 2 by 3 becomes 3 by 2. And this is what it becomes. It was landscape form. Now it becomes portrait form. Okay. Just like vectors, we can add. So this was our original M matrix. If we add 2, you can see here that we're just adding element wise 2. We can add two matrices as long as they have the exact same dimension, right? So this makes sense. We can also multiply a single matrix with a scalar. So each element is going to be multiplied. And now finally, we just like that we talked about the dot product. Here we want to talk about multiplying matrices. One matrix multiplied by the other. We know that there's a certain rule, right? The first row and the first columns give you the first element. First row and the second columns give you the second column's first element, and so on. And it's followed irrespective of whether it's a 2 by 2, 3 by 2, 3 by 3, any sort of matrix, right? So we know that it should follow this parameter, right? M cross N. And if you multiply it by something like N cross P, the resulting matrix here, what should be the dimensions of the resulting matrix from week 2's lectures?
M cross P.
M into P, correct. Good. Right. So here anyway, so here, all right. So when we do this, it gives us an output because it's doing an element-wise multiplication. And this symbol right here, the percentage, multiplication percentage, is the actual matrix multiplication method, but it's going to give you, what happened here? Let me just do this. Right. So sometimes, not always, but sometimes space is important in R. Okay. This is something you would learn with practice. So here it's just said it's unexpected something, but I know that percent multiplied percent asterisk percent is actually the symbol for matrix multiplication. So what happened? I just added spaces here so it could understand. This brings me to another thing. So we saw a few warnings in some of the commands we ran. We saw these errors. So it's very important to understand them because you would like to troubleshoot those, right? So again, with practice, you will understand what the error means. And if nothing works, the best way to deal with these errors is to Google them. Because if you have encountered an error, it's very likely somebody else has also encountered the error. So you Google it, you see what the error means and how you can troubleshoot. And then with practice over the years, you would not need to Google. You can just see, this error doesn't make sense. Okay, I'll just add a space and we'll be fine. Right? So now here it says non-conformable arguments. So we know why, because M into N and again M into N. So like 2 into 3 and 2 into 3 matrices cannot be multiplied, right? Okay. So on the other hand, if we would like just maybe, can you tell me what I'm doing here? If I write this, do you think, so what, first of all, tell me what is this? And then tell me, is this going to give me an output? We're doing a transpose and we are going to multiply transpose of one matrix with the other. So now this condition is actually going to satisfy. So hopefully This gives me an output. And here M was 2. Here also this other P was 2. So we got a 2 by 2 matrix, right? All right. So if we find a determinant, it's not going to give me because here M should have been a square matrix. You can only find determinants for a square matrix. So I'll just make a square matrix here. I'm just given a random vector A and I'll make a matrix out of it. So I want to make a square matrix 3 by 3, so 9 elements and all. I just write by row is false, so it's going to be by columns, although it should not matter. Now I find the matrix, I find the determinant, it's non-zero, so I can proceed with a few other things that I want to find. So if I want to find the eigenvectors and eigenvalues for a matrix, there's this function eigen. So when I run this, you see it says dollar values, dollar vectors. So what it sort of means is that the output of eigen has two things in it. One is values, one is vectors. And you can access the two by dollar. So for simplicity, I'll just going to save this into a variable E. So this thing that you saw here is now saved in E. This is the first part of a list. This is the second part of a list. So to confuse you a little more, I'll call this E as a list of lists, where the first element of the list is again a list. And the second element is actually a matrix. So you can see here, E is actually a list of two elements, but the first element is a list and the second element is actually a matrix. You would encounter these complicated data types in R. But the simplest part is to pick on what is important to look at here. So here it's values, vectors. So we just do E dollar vectors to get the, so if I just press this here, vectors, and just values as values, so that's fine. Now the last part here is to solve a linear system, to solve a system of linear equations. So simple one, two values, two variables. So we have A, which is the coefficient matrix. Now in this case, you need to be very careful of whether you are specifying it by row or by column. So here I have 1, 1, minus 3, 1. I want it to be in this order. I cannot transpose it, right? So when I write, So when I write this here, this is the matrix I get. And you can see that this is correct. However, if I would have written this, it would have changed, right? I got the transpose and it does not make sense. I would not be able to solve. So here you need to be very careful of specifying by row and by column. And B is my the constant matrix. The function here is solve, where the first argument is my matrix. Second argument is the vector, and it's going to give me the output. Sorry. Yeah, so I read A, B, and then I solve, and I get X is 1, Y is 5. You can solve it. Now, the only thing missing was inverse. So if I don't specify B, I'll get the inverse, right? This is the inverse of A. And with this, we come to an end of the quick recap. I just have a few more questions for you to quickly go through. So here, I think we discussed everything. Command prompt. Yes, it's very important to save the script. So we made these changes. I saved it. So there's no longer this asterisk sign here. Now directory be set. Okay, so just one more thing. You can see here it's using these forward slashes, right? So if you want to specify the directory, so one of the ways to specify the directory was using session, set working directory, and then choose a directory. The other way is through this command, set working directory, double quotes, and you can actually, you can actually start writing it the same thing. Sorry, it was documents and so on. I could actually go and do it like that. So just, I just want to mention that this uses forward slashes. Okay. Says no, the use. And we also talked about is equal to and the assign symbol. You can run commands through these different ways. Hashes are going to give you comments. Oh, one more thing. Yeah. So let's say now I actually don't want to look at any of this. Everything is a comment. So what I can do is I can individually add hashes into each of them. But if I want to add hash, I want to comment all these things, I'll write Control, Shift, and C. Everything becomes a comment. I don't want to do that, so I'll press Control Z and I just need to save it. What else? This is done. So we did install. This is something we'll probably come on to in the next lecture. So by default, all the R packages that you install, they're going to be in the CRAN repository. Just for your information. We saw that you can do it install tool, select CRAN, write the name of the package, or we can do it by install.packages, bracket, and within double quotes, you can write the name of the package. You need to load the library every time R is started. R Studio is very helpful to predict what you are typing, so you don't need to remember the exact names. Everything is case sensitive, so a small x and a capital X, they'll be considered as two different variables. You need to be very careful if at all you are overwriting variables. Initially, it's advisable to not overwrite variables because you cannot go back to the original one, right? Question mark followed by the command. This is the best way to start learning commands. So you are absolutely sure of what you're writing, what the command is doing. And here you will understand that there are some arguments which are compulsory and some which are optional. The optional ones usually have a default value with them. Okay, so this we did in our studio and now is practice time. So I hope you're still able to see my screen. So I have 8 questions with you, really quick ones. We don't need to go into our studio for that. So can you tell me which of these 4 commands, which of these 4 functions will you use to read a CSV file? A. Very nice. So that's the correct answer. Okay, I think I have the answers below, so I'll just put it in full screen. Okay, so D is a 12 by 3 table. So which of the R statements will give you all the information in the third column? All information means all rows and third column. Which of these? Again, A, right? So the row input here is empty, which means everything. 3. So here we are basically converting the sentence into R syntax, right? Okay. So what will be the output of the following R code? So X is specified as 3, assigned as 3. We are assigning the value 10 to Y, and we are saying Z is X plus Y. And we are printing Z. Output, what's the value of Z? Simple addition. Addition. Oh, there's no minus. This is assign, right? Arrow followed by a hyphen. This is not minus. Right? So it's 30, correct. Yeah. Actually, this brings me to one more thing, which I'll just tell you in a moment. Okay. So which of the following is not used for logical, is used for a logical not? You want to negate the output.
D.
D. It's the exclamation mark. Great. Which of the following R functions will be used for a one-way ANOVA? We used it a while back.
One-way test.
One-way test. Good. Very good. And V is a vector with 10 elements. And if we do summary, we'll get the statistical summary. There's one of these values that one information you will not get. Remember, we get min, max, first quartile, third quartile, mean, median. So what do we not get?
Variance.
This is just a memory base, so we don't get the variance here. We have a VAR function that can give you the variance. Okay, an R code is given, again, what the value of Z is. So you can take a pen and paper and so first of all, you can just tell me what is U here. Can one of you write it here? So let me just pen and this. Yeah. Right. So, okay. So if you can see here, Q is equal to, starting from 2, then we add 2, so we get 4. Then we add 2, we get 6, then we add 8. If we add 2, we get 10, so we will not be able to, so that is not. All right, so U is a list with these 4 values. Then what is V? It's just 1, 2, 3, 4, right? So just put a comma here, right? And then W, we are just adding 2 vectors. So how are we going to add it? Are we just going to add everything 2 plus 4 plus 6 plus 8 plus 1 plus 2? Or are we going to do it element wise? Element wise, correct. Right, so what we get is 2 plus 1, 3, 4 plus 2, 6, 6 plus 3, 9, 8 plus 6, 14. Right, so this is W. Now here it's a complicated one, so we start from the inside, right? So first of all, we calculate what is W3. So W is a list. Here we want to find the third element of the list. And what is that? What does 81 mean? We are finding the square root, not the square.
3.
SQRT, yeah. So W3 here is 9. And now we want to find out the square root of 9. Right? So that is equal to 3. So the output here is going to be 3. Okay. All right, great. Yeah. And now what is the use of the norm function? To find the length, to normalize, to inverse, to calculate the probability using normal distribution. A, right? Find the length of the vector. All right, that's it. It's got stuck. Yeah, okay. So I will keep the annotations. Yeah. So we have recorded today's lecture. We are almost on time. And the scripts that I used today and this PPT I'll share on the Google Drive. This link, I believe all of you already have. If you want, I can paste it in the chat box. So the deadline for this week's 3's assignment is day after tomorrow, 15th, Wednesday. So do submit it on time. And the next live session, where we'll be discussing week 4, is going to be on next Monday, same time. I remembered one thing to tell you. So before you go, so it's just that sometimes, so let's say I want to make thing like, so 3 plus 3, I can specify directly. But let's say I want to something difficult like this, right? So it's always advisable to, if you have a negative number, and if you're doing some mathematical operation or some functions on it, it's always good to enclose them in a curved bracket. It's just like we do in maths, right? You always have brackets to avoid confusion, to help you in which should be solved first. So yeah, so just like we sort of got confused with the assignment symbol as this hyphen as a minus sign, it's always good to have it in minus, have the minus number in brackets, just to avoid any confusion, right? So that's all. So I will stop sharing my screen now. All right. So if you have any more confusion, let me know. Otherwise, I think we're done for the day. Anything else?
In one of the lectures, I saw like Sir was converting the data frames into matrix and then plotting the histogram. Is it necessary to change the data frame into matrices before we could do histogram?
Okay, so why not we try this? So the best way to check it is to work like that. All right. So another thing is that when we are making a histogram, we actually just have a value, right? We don't really work with data frames. So are you talking about histogram or box plot?
Histogram.
So for a histogram, it's always just a list. So you neither need a matrix nor a data frame. It's just a list. So as long as you can extract the column from it. So let's say, for example, we have this column, right? So this thing here is a data frame. So let's try hist of plant growth df2. It was a data frame, so we can extract the column using a $sign. So we write control and we get this, right? That's one way. I think so. Now I'll just make a temp, which will be data dot matrix of, right? So again, temp is again the same thing, but as a matrix, right? So now if I write hist of this temp and I want to plot control. So I want all the rows of the first column, right? So I get the same thing. It's the same thing, absolutely same. Similarly, if I would have had CTRL as, so let's say CTRL is actually a list that I have, where I would have specified it using so and so values, right? Like 4.17 and whatever it was. So I could just plot his control. So for a histogram, you only need a set of values, a one-dimensional list or array.
Thank you.
All right. Anything else? If there's nothing else, then I thank you so much for staying for 2 hours. I hope you learned. If at all there is any confusion about anything, you can drop your questions on the discussion forum, and we'll try to solve it as soon as possible. Okay. All right. Thank you. See you again next week, same time. Bye-bye.